Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we will continue talking about solving CSP problems efficiently. Last time we finished talking about ordering, how to choose a next variable to assign, and how to choose a value to assign to that variable. Inshallah, today we'll talk mainly about two ideas. Actually, one concept and two ideas. The concept is called K-consistency, which is a general concept when we extend the idea of our consistency to more nodes. And then, inshallah, we'll talk about efficient solutions of CSP, especially when the structure of the constraint graph is of specific property. We'll see that we can find a solution much more efficiently than general CSP. And if we have time, we'll start to talk about iterative improvements. We'll start with K-consistency. We already know the first 2 points here, one consistency and two consistency. What is one consistency? One consistency is what we call node consistency. In this case, if we say that a node is consistent, that means that there is a value that meets the node unary constraints. So something like if I want this node to be colored blue or green. So blue and green now will be the two values that can be assigned to that node. So that's one consistency. If we guarantee that this is the case for all nodes, which is in most problems, of course, then the graph is one consistent. Now, two consistency is exactly what we discussed as arc consistency before, but here the definition is a bit different. And will allow us to extend the definition to higher order nodes. So two consistency defined this way is the following. For each pair of nodes, any consistent assignment to one can be extended to the other. So if I have a consistent assignment to that node, it will be extended to the other. What does that mean? That means that I will find the consistent value here. I will find the value here that will be consistent with every consistent value here, or each. Okay, so that's exactly what we have in our consistency. If I have a consistent value here, I will find a value here that will be consistent with that. So that's exactly our consistency, and this is called two consistency. Now, if we extend that concept to higher order of nodes or higher number of nodes, we call this K consistency. So in K consistency, if a graph is K consistent, then for each K nodes in the graph, any consistent assignment to K minus 1 nodes of them can be extended to the Kth node. So if it's, for example, 4 consistent, that means that every 4 nodes, each 3 of them, if I find a consistent assignment to them, then I find also a consistent value to the Kth node, or a value to the Kth node that will be consistent with them. Okay, so if 3 nodes are consistent, then I can find a 4th node, a value for the 4th node that will be consistent with them. If that's the case for every 4 nodes, then we call this graph 4 consistent. If it's for each K nodes, then this graph is K consistency. So this is a general notion of consistency. It's not only about 2 nodes, which is our consistency, which we discussed last time, but it can be a general definition. Of course, as K increases, we need to do more computation to make sure that the sets of nodes or the subsets of nodes are consistent. So it's more expensive as K, of course, increases. Also, if we look at this graph that we checked the last time, we found that this graph is arc consistent because all the arcs are consistent. But still, there is no assignment for that graph that is consistent. If actually you look at 3 consistent, then you will see that it's not the case that for every pair, for every consistent values for a pair of nodes, you will find a consistent value for the third. Because, for example, here, we can assign blue here and red here, and of course, we cannot find a value to assign for the third one. So this graph is not 3 consistent. It's just 2 consistent and 1 consistent, but not 3 consistent. Okay, so if we check higher order consistency, we will detect more failures that we might detect in the future in case we use less order consistency. Now there is a stronger notion of K-consistency called strong K-consistency. So a strong K-consistent graph is also K-1 consistent and K-2 consistent and 1 consistent and so on. So that's much stronger than just the definition of K-consistent. So strong 5 consistent means that the graph is 5 consistent and also 4 consistent and also 3 consistent and so on. Now, if we assume that we have strong N consistency, where N is the number of nodes in the graph, that means that we can solve the CSP without backtracking. So we can find the solution with no need for backtracking ever. Why is that? Now think with me. If it's inconsistent, that means that it's 1 consistent, right? So we can choose any assignment to any variable. So we will choose a variable and we assign a value to it. Okay? Of course, because it's 1 consistent, we can find the value. Now choose another variable, choose any other variable, and by 2 consistency, that means that there is, for that new variable, there is a value that is consistent with the first variable. Now choose a third one. By 3 consistency, there must be a consistent value for that third variable that will be consistent with the other 2, and so on. So we'll continue this way until we finish the n variables. Now we found the solution with no backtracking. Just because that the graph, we assume here that the graph is strong n consistency. Okay? If that's the case, why is that bad? Or why don't we do that always? Why don't we do that always? Faisal? Yes, of course, it will be very expensive to compute. Okay, and it might be at the same cost of finding a solution with other methods. Okay, so it's very expensive to make sure that the graph is inconsistent. Okay, so doing that computation, it might be even more efficient to do it in other ways. But theoretically, if the graph is inconsistent, then we don't need backtracking. So this is just a notion, or extending the notion of R consistency to K consistency. Now let's move on to more fun with solving CSP. We will solve special case of CSP that are of specific structure, and we'll find that we can find efficient solutions to those special structures. The first structure that we will consider today is the graph where we have the extreme case, which is independent subproblems. What does that mean? Look at this constrained graph. We'll find that this node is completely separate from that graph. Even if we have here, and let's assume that we have here other let's say that we have here other nodes. Okay, something like this. Still, this is completely independent. So this graph, or this subgraph, is completely independent from that one. That means that I can solve this one completely separately from solving that one, because there is no connections, there is no constraints between these variables and these variables. Okay? Now, how can we identify that there are subproblems that are independent like that? If you remember from studying graph theory or graphs, there is a concept called subconnected components, or connected components of a graph. Okay, so these are actually connected components, separate connected components. Each connected component of a graph is a separate CSP by itself. Now, why is that good for us? Now, suppose that a graph of n variables can be broken into subproblems of only c variables. Yani, let's say that we have 20 variables here. The graph has 20 variables. I found that we have four connected components within that graph. Each has 5 nodes. Time. If I solve these subproblems independently, would that be more efficient than solving the general problem? The general problem, to solve it, the worst case for solving n variables, each has d values, is to try all the cases, right? D values for the first one, and the d values for the second one, d values for the third one. Of course, all of them multiplied. So the worst case is order d to the power n, where n is the number of nodes and d is the number of values in the domain. So it's exponential in d. Exponential in d. That's the worst case for the general problem. Now let's see if we decomposed the problem into multiple subproblems like that. So I will just erase this. So let's say that I have here is a subproblem, here is a subproblem, and so on, and each of them has c nodes, and the total, of course, is n nodes. So that means that that means that I have how many of the subproblems? I have n over c subproblem, because each one has c. Okay, so I have n over c subproblem. Now for each one, what is the worst case complexity for each one? We said here, if we have n values, the worst case is d to the power n. So the worst case for each one of them will be d to the power c. So the total time complexity for all is d to the power c times n divided by c, because that's the number of subproblems, which is the time complexity here. Okay, now compare this with that. You will find that this one is linear in the number of nodes, assuming that c is constant, of course. Okay, so this one is linear in the number of nodes. Just let me complete, please, and then I will open the door for questions. Okay, let me continue this, and then I will take your question. So compare this with that. There is a huge difference, but you might not imagine how huge a difference is unless we have some numbers. Let's say that we have 80 nodes, and for each we can have only 2 values, and the number of nodes in each subproblem is 20. So that means that we have identified 4 subproblems. Each one has 20 nodes. The general problem, which will take order of 2 to the power 80, which is 2 to the power n here, will take 4 billion years if I just process 10 million nodes per second. 4 billion years. Now, on the other hand, if we solve each problem separately, then it will be that order, which will take 0.4 seconds. It's not even 0.4 years, it's 0.4 seconds. So imagine the difference between these two. Huge difference, huge gain in efficiency. Now, questions. Raise your hand, please, if you have any question. No questions. Okay, good. Okay, now Will that be really in practice useful or not? It depends on the problem that you are solving. Usually the problems that we are solving are not decomposable. But if it is decomposable, then of course that the solving them independently will be much more efficient than solving the general problem. Now let's move on to a simpler and more practical problem, which we call tree-structured CSP. Tree-structured CSP. What is tree-structured CSP? Tree-structured CSP is a CSP that has a constraint graph that has no loops. It has no cycles. Okay? No cycles at all, like this one. So if I have an arc here, that would be a cycle. If I have an arc here, that would be a cycle or a loop. But this constraint graph doesn't have any cycles, so it's called tree structured, and we will see very soon on the next slide why it's called tree structured. Now the claim here is that if the constraint graph has no loops, which means that it is tree structured, then the CSP can be solved on order nd square. Nd square only d square, and comparing this with d to the power n, of course, again, there is a huge difference, a huge gain in efficiency. Let's see why we call it tree structured if it has no loops. If it has no loops, then I can choose any node here, and imagine that you are shaking this graph. Take this node as a root, put it at the top, and shake this graph. If you do that, then you will find the tree structure. Let's try this. Let's say that I will take the take node B as the root. You can, by the way, you can take any node. Okay, take B. So we'll put B as the root at the top. Now B is connected to A and C. So when we shake the graph, okay, and putting B at the top, of course A will be next, and then C. Then we have also D, and D is connected to E and F. That's a tree structure. We couldn't have done this, or we couldn't have a tree here unless we don't have any cycles here. Okay? So taking any node, you can make it that way. Of course, tree means there is a parent, and for the parent there are children, and for each of the children they might have children, and so on. And every child, of course, has one parent. So we can have a tree like that if we take any node as the root. So that's actually the first step in solving the tree structure CSP, is to get a tree like that, and from that tree we order the variables so that the parents precede children. So that's exactly like doing BFS. Okay, so we'll put B. So we order the nodes from left to right so that the parent comes first before the children. So we'll have B, A, D, C, and then EF. Take it for as if we are doing BFS. Then add directed nodes from the parent to the child. So we have from B to A. We have from B to D. We have from B to C. Then we have from D to E, and from D to F. So this is the step 0 in solving the tree structure CSP, is to choose a root, shake the graph so that it will be a tree, and then order the variables so that the parent precedes children, and put the edges in a direct form like that. Here the example, so this is like shaking the graph, and here is an example where we choose A to be the root. Okay, so here we choose A to be the root, so we can order them as A, B, C, D, E, F. If we do that here, you will find that the tree will be A, then we have B, then B has C and D, and then D has E and F. And then you get this order out of it. Okay? Take the root as you wish. Any node will be okay as a root. But fix that and then order the node accordingly. Now, let me remove all of that. Or maybe, yeah. Okay, now we will put the node, the values of the domains with the variables here. So we'll put the values for each node. Okay, the domain values for each node. Okay, now the step number 1, so all of that is considered step 0. Okay, step 0. Now, step number 1 in solving this tree structure CSP is to go backward. And when we go backward, we apply our consistency on every node. So let me show you an example here. So we'll go backward. Let's see with F. What is the age going to F? It's D, right? So D to F. Now, is that consistent? Let's see. Red is okay. Green is okay. Blue is not okay here because we have to assign blue here. So this blue has to be removed. Then so F now is done. Then E. What is the age coming to E? It's from D. Is it consistent? Yes, it's consistent. We don't need to remove anything. So E is done. Then D. So we'll look at the arc BD. Is it consistent? Green is okay, blue is okay, then it's consistent. So D is okay. D is gone. Or not gone, it's done. Okay, now C. B to C. Is it consistent? Let's see. Green is not consistent because we cannot assign green and green here. So we'll have to remove this green. And blue is okay. So we are done with C. Now B, A to B, is that consistent? Red is okay, blue is not okay, so we'll have to remove blue. Now the graph is, we checked all the arcs backward and made them consistent. Okay, so this is the first step. So step 0 is to get this order. Step 1 is to apply our consistency backward. Okay, backward. For each node, look at the parent and make sure that the arc from the parent to the child is consistent. Step number 2, now that we made sure that the arcs are consistent, step number 2 is to go forward and assign consistent values. So let's see that on that example. Start forward, so we'll start from the root. We have just one value here, so we'll assign red to A. Then B, we also have one value here, so we'll assign blue. Type. Why is that assignment? Why don't we check here if it's consistent or not? Because we already made sure that it's consistent from step 1. So we are sure that for every value here, there will be a consistent value here. So we will find the consistent value anyway for every value here. Since it's just one, we don't need to even check. Now, so we choose blue here. Here again, it's just one value, so we choose green. Then now we have D. D we have two values, so we have to choose a value that is consistent with the previous ones. What is the parent of D? parent of D is not C. Okay, watch out. It's not C, it's B. So that arc, okay, we have to make sure that there will be a consistent assignment. Of course, we will find anyway, but which one? So we have here blue, here we have green, red, green, so we can choose any of them. I would choose green. Just randomly, anyone. It won't matter. It won't matter. Okay? And we will talk about why doesn't matter in the next slide. So once we choose green here, then the next one will be E. What should we choose? We have green and blue. We have to choose something that is consistent with the previous variables. We have a constraint here. We cannot assign green here. We have to assign blue. Would it be the case that we cannot find a value that will be consistent? No, for sure not, because we made sure that all the arcs are consistent already, which means that for every value here, we'll find a consistent value here. Now for the last one, we have blue here. What should we do with this? Watch out that there is no link here. The link is from D to F. Okay, so we can, of course, assign blue here because there's no blue here, so it's not a problem, and there's no link actually between E and F. So we are done with a solution. Red, blue, green, green, blue, blue is a solution for this problem. Did we need to do backtracking? No. We didn't do any backtracking. We didn't do any more arc consistency, except that we did it in a backward way. There's no backtracking. It's much more efficient than the general CSP. Now, how about the complexity? Okay, let me make sure that first that you don't have questions before we go to the complexity. Any question about this? So 3 steps here. Step 0, order. Step 1, backward, arc consistency. Step 2, forward assignment. Any questions about that? Mustafa? Wa alaikum assalam wa rahmatullahi wa barakatuh. It might change. It might change, but still we will find a solution. There might be cases, by the way, that there is more than one solution. Here, as you saw, we could have chosen red here, right? We had that choice, I think. Right? I chose randomly green, so I might choose blue, red here. I will have another solution, but it's okay. We will find a solution by all means if step 1 was successful. If we make sure that all arcs are consistent, then for step 2 you are guaranteed to find a solution. But as you said, if we choose the root to be another node, we might find other solution. But still you will find a solution for sure. Did I answer your question, Mustafa? Okay. Any other questions? Ghanem? Okay, so you have another problem now that I cannot imagine, but if it's tree structure, then I can solve it this way for sure. Okay. York. Any other questions? Should we move on? طيب, why the complexity is ND square? Any idea? So the complexity here is ND square. What is N? N is the number of variables, and D is the number of values in the domain. Why is it n d square? Any thoughts? Just try with me. But why there is d square here? What is the operation that needs d square? Fahd, do you want to pick up the mic? Fahd? Okay, Ghanem? The entire nodes, the entire set of nodes. Okay, yes. Okay, so d square comes from checking the arc consistency, the consistency of one arc, right? Because we check d values in the tail versus d values in the head. Okay, طيب, why do we have n of these? يعني it's n times d square, right? So it seems like there are n arcs, okay, and or order of n arcs. For each we have d square. Why do we have n arcs to check Ghanem? No, but we are done with d square. We said d square because this is the complexity for checking the consistency of one arc. But having n here means that we have order of n arcs. So why is that? We go through n nodes here, but is it the case that for each node we have just one arc to check? So each node can have more than one arc coming to it, because here if you look at this pseudocode, it says that for I equal n to 2, so backward, okay, parent of xn and xn, so parent of this node, which is d, and that node. So is it always the case that we have just one arc coming to a node, or it can be more than one arc? Coming, incoming. Okay, type. If okay, in a tree, remember that we said that this is tree structure, right? And I showed to you that it can actually look like a tree, right? It's a tree. So in a tree, is it possible for any node to have two parents? In the tree data structure that we all studied before, is it possible to have two parents for the same child? Can we imagine something like this? Let me show you. Can we have something like this? In a tree? Can this be called a tree, for example? What do you think, Ghanem? No, okay? No, so we don't have this, of course. In a tree, there is one parent only for every node except the root, of course. Okay, so that's why we have, if we have a tree structured CSP, then this order, or this tree, actually this is a tree, but it's linearized. In this tree, we will only have one incoming arc for each node. One incoming arc for each node. Okay, so we have order of n arcs each of them will have d square. Okay, thanks Ghanem. So that's for the backward step. For the forward step, we'll just need to assign one value for each variable, right? So one value times times n, because we have n nodes. So it will be order n, or in the worst case, n times d if we want to try all the d values. Still nd is less than nd squared, so the total runtime is nd squared because of the backward step. Okay, so this is why it is nd squared here. Now, two claims about this tree structure. The first one, and I think they are related to the discussion that I just had with Ghanem and with all of you. The first claim, after backward pass, all parent to child arcs are consistent. After the backward pass, all parent to child arcs are consistent. Or in other words, we don't need to recheck any arc if we do this linear backward pass. Right. Let me discuss this with you with an example. Let's look at this arc. Okay, let's look at this arc. After I'm done with this arc, okay, I might remove some values from D, right? Okay, now I'm done with this arc, so this arc is consistent. When will I need, generally, if I have an arc like that, from that node to that node, okay, let's say x to y, and I made sure that this arc is consistent now, but I will do some other checks in other arcs. When will I go back and say that I have to recheck that arc? When can that happen? Any idea? We said that last time, Hamza? No, let's just focus on this case, Hamza, x to y. So when will be the case that we need to recheck x to y? Generally, don't worry about this graph now. Exactly. If it happened that we changed the values in the domain of y, okay, here, so let's say that we have multiple values here. If we removed some of them, we might make, by removing these values, we might make this arc inconsistent now. So we'll have to make sure that there will be values here that will be consistent with values of x. Type. Will this case ever happen here? After we check D to F, will it ever happen that the values of F change? When can that happen? Only if we have other, only if we have values that are changed here in F, right? Will that ever happen in the tree structure? No, it will never happen. It will never happen, okay? Because we will not consider F anymore after we are done with df. We will not consider F anymore, okay? Because خلاص, we will consider the parent of F, but remember that in a graph, we don't even have this case. In the tree, sorry, we don't have even that case. We don't have even an arc that is coming to F, other than just one. So after we are done with F, the values of F will never change. Okay, so each, if you look at this now, each x to y was made consistent at one point, and y's domain could not have been reduced thereafter, because y children were processed before y. Yani F, once we process F, there is no, we will not process F to something else here. Okay, because we assume that the children of F are processed already, خلاص. So we will not go back and change f, because these are the cases where the values of f might change. If we found that this arc, for example, is inconsistent, then we will change a value here in f. If we do that, then we have to go back to df. But we are done already in the backward pass. We are done already with these links. So we will never go back to f, and thus when we go backward, everything, all the arcs will be consistent. Of course, if there is a solution to the problem. Okay? Is that clear? So going backward, because of the order of the arcs that we are checking, we always check the arcs that are for each node backward, which means that we will process the child first before the parent. So once we process the parent, we are sure that all the children of it are already processed, which means that it will never, after checking that node, it will never change. The values of that node will never change, and thus every arc after checking it, we will not have to recheck it. So that's the first claim. The second claim, if parent to child arcs are consistent, then forward assignment will not backtrack. Forward assignment will not backtrack. Now, remember, when do we backtrack? We backtrack if we found that in one variable, we don't have any value in the domain that will be consistent with the previous assignments. But we just made sure that every node, the arc coming to it, which is unique, because it's a tree, is consistent. So any value that I will assign in the parent, it has a consistent value in the child. And this is for all arcs. Okay? So we will always, after we are done with step 1, with the backward pass, if it's successful, which means that we made sure that all the arcs are consistent, then any value that I will pick at any node will be consistent with its child. We will find the value in the child that is consistent. Okay, so we will just go forward and for sure find an assignment for the variables that will be consistent, and thus we will not need ever to do backtrack. You can do that with induction if you remember mathematical induction, but even simply by this logic, it's clear that since we guaranteed the consistency of all arcs, then moving forward, assigning any value to a node, you will find for sure a value in the child that will be consistent with it. And we saw that, of course, in the previous example. Okay? Any question about this? Okay, if there is no question, then we'll move forward to the next idea, which is improving the structure. Now that we know that there are special cases in CSP that can be solved efficiently, how can we exploit that? Will we find many problems that are tree structured already? Actually, probably not. Okay, most of the problems will not be tree structured. Does that mean that what we just discussed is rarely used? The answer is also no. And the reason is that we can convert a problem to a tree structured problem. Here is how. We will do what we call conditioning. So what is conditioning? First, look at this graph. Look at this graph. Okay, forget about this one. Look at this graph. Is this graph tree structured? Is this CSP tree structured? Of course not, because we have loops here everywhere. Loop here, loop here, loop here, loop here. So it's not tree structured. The question is, can we convert it into a tree structure? Yes, look at this right side. You will see that if we remove this node, then the graph will be tree structured. If we remove that node, we'll get this. Now we can solve this efficiently, right? Solving this efficiently, does that mean it will solve the original problem? Of course, in a straightforward way, no, because we changed the problem. These two problems are actually different because we just removed this variable from here, so we assume that it's not there. But the right way to do it is to do what we call conditioning. So for that variable, that if we remove, the problem will be tree structured, we assign a value to it and prune the domain of the neighbors of that variable before we remove it from the graph. If we do that, then the new graph is still different problem, but it is related to the actual problem. So solving the new problem, that is much easier, we can extend it easily to solve the original problem. Actually, it will be very straightforward way of moving back to the original problem. So this is what we call conditioning. Instantiating a variable, which means assign a value to a variable and prune its neighbors' domains. So if I assign the value red here, for example, then I should remove red from here, red from here, red from here, red from here, red from here. Once I do that, then I can remove that variable and keep the new values of the domains for the other variables, solve this problem using the efficient algorithm that we just saw, and then add to the solution the value of red to SA. That will be a solution to the original problem. Now, we have another concept, generalizing condition, called cut-set conditioning. So conditioning is not about the tree structure in particular. Conditioning is just assigning, instantiating a variable by a value and propagating that value to the neighbors. Now, cut-set conditioning is to do this instantiation, but on a cut-set nodes. What is a cut-set node? The cut-set node or cut-set set of nodes are the nodes that if we remove from the graph, then the graph will be a tree, will be a tree structure, or in other words, it will not have loops. So in this graph, removing that node will make the graph with no loops. It will break all the loops or all the cycles, and thus we can have a tree structured CSP. We will talk about this runtime complexity next lecture, but let me show you what I actually mean by cut-set conditioning before we end the lecture. If we focus again on the same constraint graph, then to solve it in this way, we have to choose a cut set. The cut set is the minimum number of nodes for which the graph will be a tree structured if we remove them. So the minimum number of nodes here that if we remove, the graph will be tree structured is SA. So think about breaking the loops. What is the minimum number of nodes here that if we remove, we will break all loops? Of course, this is just SA. So in this case, we will assign a value to SA. But which value we should assign to SA? We don't know in advance, right? So we'll have to try one by one. So we'll instantiate the cut set with all possible ways. Let's say that we have the three possible values, blue, red, and green. So we'll try blue first. Okay, so we'll not try all of them at the same time, of course. We'll try one by one. Let's say that we'll try blue for SA. So that means that we can remove, we will remove the blue from all the neighbors, which means here computing the residual CSP. Now we have this tree structured CSP. But remember, the link between this and the original problem is that we will have to assign blue to SA at the end if we found a solution. Now we will solve this problem using the efficient algorithm that we just discussed today. If we found a solution here, if we found a solution for this problem, then we are done, because now we found a solution to the original problem, which will be this solution plus assigning blue to SA. If we couldn't find a solution for this, then we'll try the other value, which is red to SA. Now we reduce it to this tree structure, solve it efficiently, found a solution, done. If we didn't find a solution, then we go to we go to green for SA, and we try to find the solution. Okay, so it will be a step by step this way. Unfortunately, we ran out of time. We will start by this again, inshallah, next time. It's just an introduction now. Last question, Saad. The cut set itself? Generally, I don't think. No, they don't have to be adjacent to each other. No. But when you instantiate them, you have to instantiate them all together. Yani, if we have two nodes that are in the cut set, then you have to try all possible combinations of them. Yani, instead of having 3 values here, you might have 9 possible values. Sorry, not none. 9. I meant 9. 9 possible values. Okay, and you try each one in sequence, because you will have to assign pair of values to these two variables. Okay, you're welcome. Okay, we'll stop here and talk to you inshallah on Tuesday. As I emailed you yesterday, the homework now is due tonight, and the quiz will be inshallah next lecture, and still will have the same coverage. So today's lecture will not be in the quiz. Okay, still we will cover up to the end of last week. Talk to you inshallah next time. Assalamu alaikum wa rahmatullahi wa barakatuh.